Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 2 from the October-November 2023 mechanics paper from Cambridge 9709. This is paper 4, variant 3. And here we have a question which involves a machine for driving a nail into a block of wood, causes a hammerhead to drop vertically onto the top of the nail. The mass of the hammerhead is 1.2 kilograms and the mass of the nail is 0.004 kilograms. As in the diagram, the hammerhead hits the nail with a speed of v meters per second and remains in contact with the nail after the impact. The combined hammerhead and nail move immediately after the impact with the speed 40 meters per second. So we have a situation which I'll write on this as before. This is the situation before. I'll use the diagram here for the situation before the hammerhead hits the nail. So this is like a question which obviously involves something to do with momentum. Okay, so we need to find the speed of the hammerhead before the impact, which is the hammerhead hits the nail with the speed. So we need to find the speed before of the hammerhead. We know the speed before of the nail is 0. That's 0 meters per second, and that's v meters per second. That's before. Okay, and those are the masses before. And if we think about what happens afterwards, so I'll just make a little, division there. Now afterwards, the hammerhead and the nail will be like one object. So I'll just draw it as one object. Okay, combined mass would be 1.204 kilograms, hammerhead and nail together. And they have a combined speed of 40 meters per second. 40 meters per second. So this is after. Okay, so what we can say is the total momentum before, by the conservation of linear momentum, the total momentum before and the total momentum after the collision basically is the same. So the total momentum before is the momentum of the hammerhead, which is 1.2 times v, plus and we're going to take down as positive here because it's moving down. So 1.2 times v plus, and we're going to have the momentum of the nail, which is going to be 0. It's basically going to be the mass times 0, so it's 0, equals the total momentum afterwards, which is the combined mass, which is 1.204 times 40. Okay, so we can say that v is equal to 1.204 times 40 over 1.2. Now, very important here, which we have to be very careful about. It says calculate v. Now, a lot of people will stop there. They won't read the whole question. They'll say calculate v. Okay, I'm going to find what v is, and they'll write v down, and they'll most likely write it down as a decimal. Okay, if it doesn't come out as an exact number, they'll normally write it as a decimal. Okay, but the question says very clearly giving your answer as an exact fraction. So when we find the value of v, we have to give it as an exact fraction. So we're going to put this in our calculator, 1.204 times 40 divided by 1.2. And that gives us 602 over 15, which is how we leave the answer. What happened to my pen? I don't know. So 602 over 15. Okay, so that's the value of v. V is in meters per second, so we just have to write v equals 602 over 15. That is the answer to part A. Okay, so that's important for us to understand. They don't want us to write this as a decimal. If you wrote this as 40.1, you will lose marks for this. Okay, you will definitely lose marks for this because it says give your answer as an exact fraction. That's A done. So you don't want to be throwing marks because you didn't read the question properly. Now for part B, it says the nail is driven 4 centimeters into the wood. Find the constant force resisting the motion. So now the nail, let's say it's the nail and the particle or the hammerhead together, right? It's driven into the wood. Okay, so basically we can say that the forces acting on the hammerhead and the nail are its weight, which acts vertically downwards, and also the resistance force of the, basically it's going through a surface. So there's resistance to its motion. So the weight of the object is 1.204 times g, and the resistance forces are. So we're going to find the constant force resisting the motion. Okay, so now we're going to find what R is. So what we know about this object here, it's gone 4 centimeters. It's going to go 4 centimeters into the wood. So it travels a distance of 4 centimeters. So let's say this is the surface, and this is how far it goes down. So that distance is 4 centimeters. Okay, so that distance here is 4 centimeters. That's how far, how deep it goes into the ground, 4 centimeters. All right. Now, we also know that it starts off going with a speed of 40 meters per second. That's the speed of the object together with the nail after the impact. So that's what its initial speed is going to be as it enters the wood. And when the nail has gone 4 centimeters into the wood, okay, now 4 centimeters first, we have to be careful because this is in centimeters. We want everything in standard units, SI units. So we're going to write that as meters, 0.04 meters. That's one thing that's important for us to do. Now, the other thing is, it's going to go into the wood, and it's of course going to come to rest. So by the time it's got to the bottom of this 4 centimeters, it's going to be going at a speed of 0 meters per second. Okay, so now what we can do is, if we want to find the force, we know that the resultant force is equal to the mass times the acceleration. Now, I know the resultant force is 1.204 g minus r. Okay, but I don't know the acceleration. But because I've got this information here, and as it's a constant force, so the acceleration will be constant. If there's constant acceleration, which of course here it will be deceleration because it slows down, that means we can use the Suvat equations. So we can use the Suvat equations. Now that's one way. We can also use energy, the work energy principle to answer this, which I'll do in at the end of the question. I'll show you how to use work energy principle also to answer the same question. It doesn't specify here, so we can use either method. Right, so I'll show you first this method, and then I'll show you the work energy principle. So what we can do here is we can find the acceleration because we know that it's traveled 0.04 meters into the ground. We know the initial speed was 40. We know the final speed was 0. We want to find the acceleration. We don't need to know what the time is. So we've got these four to deal with, S, U, V, and A. And if we look at our formula sheet for Cambridge, it's there. You got V squared equals U squared plus 2AS. So we can say that 0 equals 40 squared plus 2 times A times 0.04. So we're going to have minus 1,600 divided by 0.08 equals A. Okay, because you're going to divide by 0.08. So A is going to be, of course, negative because it's decelerating. That's why it comes to rest. You can have minus 1,600 divided by 0.08, which gives us minus 20,000 meters per second squared. So that's the acceleration. So now we can use the fact that the resultant force Fr equals ma. So the resultant force is the force acting down, which is the weight, which is 1.204 g, minus the resistance force, which is acting upwards. We're taking down as positive here, of course, because it's moving down, equals a mass, which is 1.204. Oops, be careful here. 1.204 times the acceleration, which is minus 20,000. So here we can see here, if we rearrange this, we have 12.04 because g is 10 plus this value here, which I'll just write as this for now, because it's going to become plus positive. Why? Because you're going to add it to both sides, and that's what r is equal to. Just rearranging it so that r goes on this side, that goes on that side. You have to add this to both sides to give it, of course, it's going to become positive here. So r is going to be equal to when we finally calculate this, it's going to be it's going to be basically 12.04 plus 1.204 times 20,000. 20,000, and that gives us 602301. 602301 over 25, which we can write. It doesn't mention it as a fraction here. You can leave it as a fraction, that's fine. But we can write this as, if we want to, we could write it like this if we want to as well. 24092, 24092.04. But best to write it to 3SF here, although we could consider an exact value. We can write it to 3SF as 2410. So 24,100 newtons. That is the value of the resistance force acting on this particle or this system as it's going through. All right, so that's the answer to the question using SUVAT and using the resultant force. And we can also find the answer to this question using the work energy principle, which I'll show you. Okay, so we'll just do the same question using the work energy principle. So what we know with the work energy principle is what we say is that kinetic energy at the start plus the potential energy at the start plus the work that goes into the system is equal to the kinetic energy at the end plus the potential energy at the end plus the work that comes out of the system. Now, the work going into the system will be some things like driving forces and so on, and the work coming out of the systems are things like resistance forces. So with this object, which is being, pushed into the ground, okay, what's happening at the beginning of its motion? It's moving with a speed of 40 meters per second. That's at, let's call that point A, and this is point B. It's moving at 0 meters per second. Okay, its distance it's moved is 0.04 centimeters, okay, down. So if we take this as our zero level, so we take this as zero potential energy, okay, then we can say that at the start, which is A, okay, this is A, and this is B, the kinetic energy is a half times the mass. Now remember, the mass was 1.204 kilograms. That's the mass. So a half times, I'll write it like this, mv squared plus the potential energy, which is mgh, plus the work in, which is going to be 0. So I'll write kinetic energy is a half mv squared and potential energy is mgh. So I'll save us something to write it there. So in this case, at the start, it's a half times the mass, which is 1.204, times the velocity squared, which is 40 squared. And the potential energy at the start is going to be, it's m, which is 1.204, 1.204 times g, which is 10, times h, which is 0.04, plus the work in, which is 0. There's no once it's been hit, there's no driving force now, equals the kinetic energy at the end. Well, it's not moving at the end, which is 0, plus the potential energy at the end. Well, it's at the 0 point we call 0 level of potential energy, so that's 0, plus the work out, okay, and that's what we're looking for. The work out will help us find the resistance to motion, okay. So we can say that the work out is going to be equal to this. So let's work out what this is. We have 0.5 times 1.204 times 40 squared plus 1.204 times 10 times 0.04, and that gives us 963.6816. 963.6816 joules. That's a work out. And we know that the force resisting the motion, we know that the work done is equal to the force times the distance. Okay, so we're going to have the work done is equal to 963.6816 equals the force that we're trying to find times the distance that it's moved through, which is 0.04. So we can say that the value of F will be 963.6816 divided by 0.04. And that should give us the same answer. Divide by 0.04. And we can see we get exactly the same answer that we got before, which is 602,301, 602,301 over 25, which again, we can round it to 3SF if you want, 24100, 24100. Okay, that is newtons. Okay, so there's the answer. So that's going to be like, we can say the resistive force. Let's change this to R. Okay, so we have the answer now to the question. So exactly the same answer using the work energy principle, where the kinetic energy at the start and the potential energy at the start and the end will be equal to each other. But if there is some external forces like resistance or some other type of force going in or out, we have to use that to balance them out. So here there's no force going into the system once it's been hit, but as it's going through this distance, there's a resistance to motion, which is going to be included with work out. So that's the only thing that we don't know on this side. Everything else is zero on that side, so we can answer the question. All right, so that, remember, work out is not the resistance to motion, that's the the work done by the resistance. Okay, they're asking us to find the force, so we have to then divide it by the distance it's moved through, and that gives us the answer to the question. So that's an alternative way of answering part B of this question. Other questions from this particular paper can be found in the playlist that will appear here in the top right corner, and other questions from the topic of, I guess this is to do with momentum, and also it will be to do with SUVAT, okay, constant acceleration. I'll also put it under, in fact, I'll put this under dynamics. Sorry, this is under dynamics, you could say. And then you can also put it under work energy. I'll put it under there as well. So all of those playlists will include this question. Thank you for watching, and see you soon.